There are a few different ways to approach these types of problems. In general, I think that they recommend in the textbook to use prime factorization. I would say that's probably a more difficult method where you have to break everything down by all of its factors. I think the easiest way to approach these types of problems is to have your list of common squares. And if, for instance, I'm trying to find what's the largest common square that goes into 50, start at the number, the first number you see that's less than 50, so 49, and put into your calculator 50 divided by 49. Since it gives me a decimal, not a whole number, I go to the next number on my list. 50 divided by 36. Again, I get a decimal, I go to the next number on my list. 50 divided by 25 gives me a whole number too. That tells me that 50 is 25 times 2, where the answer to the question is 25, because 25 is the largest of my perfect squares that goes into the number. If I see 162, then I can start at 100. 162 divided by 100 doesn't give me a whole number. 162 divided by 81 does. It gives me 2. So this would become 81 times 2, meaning the answer to my question, the largest perfect square that goes in, is 81. Notice that if I started at the start of my list, 9 would have also gone into 162. It would have gone in 18 times. If I thought 9 was the largest factor that went in, I would get the question wrong. That's why I want to start with the higher squares and work my way down, as opposed to starting with the lower squares and working my way up. If I'm looking for 20, I start here at 16. 20 divided by 16 is not a whole number. 20 divided by 9 is not a whole number. 20 divided by 4 is the whole number 5. So this would become 4 times 5, meaning the largest perfect square that goes in is 4. For 147, it's bigger than my largest square, so I can start here. 147 divided by 100 gives me a decimal. 147 divided by 81 gives me a decimal. 147 divided by 64 gives me a decimal. 147 divided by 49 gives me the whole number 3. So this is really 49 times 3, which means 49 is the largest perfect square that goes in. I'm going to show how to do these next 3 problems using the prime factorization method, but again, I'm going to remind you that I think the best way to do them is the way that I just did these 4. Look down your list of perfect squares, see what goes in. So if I wanted to do the prime factorization of 12, I could break 12 down into 3 times 4. Since I can break 4 down further, I'd have to, so this would become 3 times 2 times 2. Each of these now is a prime number, meaning they can't be broken down any further. I see there's one repeated factor, that's the 2. The repeated factor comes outside of the root, so essentially I have the root of 3 times 2 times 2. If anything is happening twice under a square root, it comes out once. So the 2 is happening twice, it comes out once, and then what's left behind is that root of 3. That's why my final answer here would be 2 root 3. When I try and break down 200, it's 100 times 2, but 100 is really 50 times 2, still times this 2, but 50 is really 25 times 2 times 2 times 2, but 25 is really 5 times 5, now times 2 times 2 times 2. So again, I can take out anything that is a repeated factor. Here this 5 is a repeated factor, so the 5 can come out front. This 2 is a repeated factor, so the 2 can come out front. I've now gotten rid of 2 things that had pairs, and what's left behind is that 2 that has to stay in the square root. 5 times 2 gives me 10, so my final answer here would be 10 root 2. For 75, I could break that down into 3 times 25. I could break 25 down further, so it becomes 3 times 5 times 5. The 5s can come out of the root as a 5, since there's a pair of them. That leaves behind the 3 still under the square root symbol. So these would be my answers, and this is what's meant by the prime factorization method. If this is easier for you, definitely use it. It's a great way to do these problems, but I'm going to show you how I'd use my method of going back through the numbers to do D, E, and F. So for D54, The next smallest number is 49. 64 would be too big. We're always looking for something that would give us whole numbers. So we have to divide this 54 by something smaller than 54. When we divide by 49, we get a decimal. When we divide by 36, we get a decimal. 25 gives me a decimal. When I put 16 in, I get a decimal. When I put 9 in, it goes in evenly 6 times. What that really means is I can break this down into the root of 6 times the root of 9. But we know what the root of 9 is. The root of 9 is 3. So this becomes 3, and what's left behind is the root of 6. If I try to do the root of 8, that would start right here because 9's too big, so I try 4. 8 divided by 4 is 2. I can break this up into the root of 4, root of 2. That root of 4 is a perfect square, comes out as a 2, and it's left being multiplied by this root of 2 that's left behind. When I try 48, 36 doesn't go in, 25 doesn't go in, 16 does go in. It goes in 3 times, so this can be split into root 16, root 3. Root of 16 is 4, so my final answer is 4 root 3. When we're asked to simplify these square roots that involve variables, basically we want to take out the even power of the variable and leave behind one of the variable if it's an odd. So in other words, x to the 7th, I'm going to split up into the root of x to the 6th times the root of x to the 1st. The reason I do that is because when I take the square root of an even number, it really becomes x to the 6 divided by 2, and then left behind is this root of x. 6 divided by 2 is 3, so my final answer is x cubed, the root of x. When I do it for the root of x to the 15th, I break it down into the root of x to the 14th, the root of x to the 1st. Root of x to the 14th is x to the 14 divided by 2, and the root of x stays behind. 14 divided by 2 is x to the 7th, so it becomes x to the 7th root of x. For C, I want to break this down into 3 parts. The first part is the root of 9, which I know to be 3. The second part is the root of x squared, which would become x to the 2 divided by 2, or just x. Last thing that's left is x to the 1st power, which stays under the square root. So my final answer becomes 3x root x. In problem D, I can take root 64, I can take root y to the 4th, and that leaves me with root y. Root 64 is 8, root of y to the 4th becomes y to the 4 divided by 2, and then I still have this root y in the problem. That makes my final answer 8y to the 2nd power, the root of y. In part E, I already have this 2x out front that I need to keep in the problem. Then I have the root of 36. All of the x's, since it's even, can all go under the same root, the root of x to the 8th. The y to the 7th I'm going to need to split up. The part I can take the square root of is y to the 6th, which leaves behind just the root of y. So this 2x still in the problem. The root of 36 is 6. The root of x to the 8th is x to the 8 divided by 2, or x to the 4th. The root of y to the 6th is y to the 6th divided by 2, or y to the 3rd. And then there's still this root of y in the problem. 2x times 6 gives me 12x times x to the 4th. But when I take x to the 1st times x to the 4th, it becomes x to the 1 plus 4, or x to the 5th. So this gives me 12 x to the 5th. I also have this y to the 3rd and this square root of y. So my final answer is 12x to the 5th, y to the 3rd, the root of y. When I go to simplify these cube roots, I need to look at the number separate from the variable. Here, when I'm trying to break up the cube root of 24, I'd want to go down my list of perfect cubes. 27 is larger than it, so the first perfect cube I can try to put in is 8. 24 divided by 8 gives me 3. So I can break this down into the cube root of 8, cube root of 3. I then can take the cube root of x to the 9th and the cube root of z to the 18th. In this case, I'm not looking for them to be even or odd. I'm looking for them to be multiples of 3. Both 9 and 18 are multiples of 3, so they're not going to leave anything behind. When I take the cube root of 8, that just becomes 2. This cube root of 3 stays in the problem. I can't go any further with that. This cube root of 9 becomes, or x to the 9th I should say, becomes x to the power of 9 divided by 3. 9 divided by 3 is 3. This z becomes to the power of 18 divided by 3. 18 divided by 3 is 6. So, outside of the root, I have 2x to the 3rd, z to the 6th. 2x to the 3rd, z to the 6th. Still under that cube root, I have this 3. So my final answer is 2x to the 3rd, z to the 6th, the cube root of 3. For part B, the same idea. I need to find what's the largest perfect cube that can go into 250. So the first one less than it is 6 cubed is 216, but 250 divided by 216 doesn't give me a whole number. The next cube below that is 125. When I do 250 divided by 125, I do get a whole number, specifically 2. So I can break this up into the cube root of 125, which is a perfect cube appearing on my list, and the cube root of 2. This y to the 24th is something I can put all under the same radical because 3 does go evenly into 24. If, for instance, this had been y to the 25th, I'd want to break it up into the cube root of y to the 24 times the cube root of y. But in this case, I can find the cube root of that whole variable expression. So the cube root of 125 is 5. Cube root of 2 I can't reduce in any way. Cube root of y to the 24th becomes y to the 24 divided by 3, which is just y to the 8th. So I can write this answer as the outside's 5 times y to the 8th, 5y to the 8th, times what's left under the radical. In this case, the cube root of 2.